Hello, kids. So let's see. Put this down here. Yeah. We started in class today looking at a case where we had a collision that was not a one-dimensional thing, right? We've done a lot of one-dimensional or several one-dimensional cases where an object bumps into an object that's moving this way, and then they stick together and end up going that way. That's all in this dimension. All right. What we want to start talking about now are collisions at angles, or two-dimensional interactions between things. All right. So we might have a case. Take the example of a standard billiard shot. Right. We're trying to put this 8 ball in the corner pocket over here. So we shoot a cue ball at it like this. The 8 ball goes that way. The cue ball goes this way. And now we have not only motion in this direction, but we have motion in this direction. This becomes what we call a two-dimensional interaction. Okay? So we'll start right off the bat with an example. Thanksgiving, rapidly approaching, of course. So we're going to talk about this turkey delivery truck, and we're going to drop 20 tons of turkeys into this truck from 8 meters up. It's a 40-ton dump truck. It's moving along at 15 meters per second. And we're going to say that the truck is coasting. All right? Oh, yeah, coasting along. So we're saying that he's got nice frictionless bearings in the wheels, and he's not on the gas, so we don't have the interaction of the engine, really. It's just this cart, this truck just rolling along. Turn it up. Hang on. Wait. Yeah, the turkeys drop into the truck, and the truck keeps on going. All right, the question is, what's the truck's speed now? All right, well, this is not the case we did before where things move this way and things move this way. Why this delay? What's going on here? It's a little bit different. Okay, what we are going to say, though, is, if we say that the total momentum before the interaction and the total momentum after are the same thing, this means two things for us. One, it means that the net momentum in the x direction is conserved, and the net momentum, come on, man, in the y direction is conserved. Should be a y there. There you go. Okay, so really, just like saying, remember when we did equilibrium, we said equilibrium means net force is 0. Well, that means net force in the x and the y are 0. Here we're saying, this is a condition that has to be true, that momentum's conserved. That means in all directions. Okay, so if we want the truck's speed after the birds are loaded, that's an x direction thing. Okay, so what we do is say m1 v1 initial x plus m2 v2 initial x is m1 v1 final x plus m2 v2 final x. And we'll call m1 the truck, 40 tons. We'll leave it in tons. And we'll call the m2 the turkeys, 20 tons. So we're going to have some interesting units. It's going to be ton meters per second, but that's okay. Normally it would be kilogram meters per second. Well, here's the dealio. The truck, yes, has an initial horizontal velocities. The turkeys do not, right? The turkeys are moving vertically, right? Just before the interaction, here's m2 v2 initial. Notice it's all in the vertical direction. Okay? Now, this is an inelastic interaction. Okay, so what we can end up writing this as m1 v1 initial x is m1 plus m2 v final x. Oops. Okay? But yes, the turkeys are moving, but not in the horizontal direction. Fair enough? It's literally like the truck collided with stationary, as far as x direction stuff is concerned, it's just like the truck collided with a stationary chunk of turkeys, all right, blob of group of turkeys. far as the horizontal direction is concerned. All right, so V final x m1 v1 initial x divided by m1 plus m2. So that's, let's see, 40 times 15 is 600 divided by 60 is 10 meters per second. Okay? Now, is there another question here? Ideally there is. No, there isn't. But what we should say is, what about the y direction thing? Well, in the y direction, really, we can say that momentum is not conserved. Okay, I'm going to write that. I'm going to say that initial momentum in the y direction is not equal to final momentum in the y direction. Right? Because initially is, again, right before the interaction, initially we have this. That's the only initial vertical momentum. Right? Afterwards, there's none. Because in the end, you have truck and turkeys just moving this way. So the final y momentum is 0. And the net, well, how about this? The initial vertical momentum is m2 v2 initial y. Well, that's not equal to 0. So momentum in the y direction is not conserved. So the question is, why is that? What justification do we have? Well, it's because the truck's on the ground. The truck is not free to move in this vertical direction. Well, really, there's a force that the ground exerts on the truck. All right? And yeah, there's a force that the truck exerts on the ground, but the ground is, quote unquote, not free to move. So we do not have a conservation in the vertical direction, but we do in the horizontal. Okay? Okay, now next. Let's look at this another inelastic case. We could do, well, the one we did in class in our little lab is an elastic case. They can be a real pain, but this inelastic case is a pretty common way to see this thing, to see these questions written. So we have this running back running at this speed, hit at a right angle by a linebacker moving at that speed, and they fall together, so that makes this inelastic. With what speed and in what direction do the two travel after the collision? Well, here's what I'll do. Let's call this, we'll say that our running back is going this way, and our linebacker is going this way. Okay? Well, they collide, so this is kind of initial, right? And I'll say that after that, is this thing, do I have a diagram of this? Nope. Whoop, whoop, whoop. Yeah, blah, 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 some words here. Let me move my diagram. Okay, so we have, let's see, sorry. So running back going this way, linebacker going this way. That's before the interaction. Afterwards, two objects stick together, and now they're moving, somewhere in that direction. Okay? Well, kind of two ways we can do this. One way is we can, well, I guess we'll just stick with this. All right? The big deal is that, each of these two initial momenta, here's momentum 1 initial, or really momentum of the running back initial. Here's momentum of the linebacker initial. Well, those are two vectors, right? And this vector here is the total final momentum. Well, really, it's the momentum of the running back plus the linebacker final. All right, well, our statement that momentum, the vector quantity momentum, is conserved means that the vector momentum initial of the linebacker plus momentum initial of the running back, those two vectors added up have to be equal, come here, to the total final momentum. All right, now, we can't just do this. We can't just go M linebacker, don't write this down, V linebacker initial plus M running back, V running back initial. You can't just do this because this is not a one-dimensional thing, right? Which way is the positive direction? Well, this guy's moving this way and this guy's moving this way. Okay, but what we can do is say literally that this vector, momentum of the running back initial, plus this vector, momentum of the linebacker initial, well, those vectors added up have to give us this, the total. Well, this really is the total initial momentum. So it has to be equal to, of course, the total final momentum, if momentum is conserved. So to find total initial momentum, which is the same as total final momentum, what we can do is use the Pythagorean theorem. The magnitude of it, at least, is that squared plus that squared. Make sense? Right? This is a vector addition. I don't know if I should put this vector sign here because really we're finding the result. Really we're finding the magnitude of that vector. All right, but that's how we find the magnitude. So here we would do, let's say that the net initial, which is equal to the net final, is the square root of, well, now we're mass running back, velocity of the running back initial, square that, plus mass of the linebacker, velocity of the linebacker initial, square that. Okay? Move. Good. Oops. Now, so that's going to come out to, we're going to do it then. Oh, man, look at that. Not have that happen. That's better. Let's say that that means this. I'm just going to write it as final momentum is, let's see, running back. 75 going at 8.25 squared plus 95 times 4.5 squared equals square root equals, so I get the final momentum is 752 kilogram meters per second. Okay? Well, notice the question is, what speed do they end up going at and in what direction? Well, notice that the final momentum is mass of the running back plus mass of the linebacker times their final velocity. This is inelastic, right? So the final momentum is the two things added up, moving at that speed. So if we find the final speed, divide that final momentum by the sum of their masses. So divided by 75 plus 95, in parentheses, of course, and we get that their final speed is 4.42 meters per second. Okay? Now, in what direction? Well, the direction of momentum and direction of velocity are always the exact same thing, right? You know, if the momentum is this way, that means it's because the velocity is this way. Okay, so we can find that angle. I would say that theta is the inverse tangent of, in this case, linebacker initial over running back initial. That's a R, not a 2. Okay, so that, again, you got to use their what do you call it? Their full momenta. So that is, let's see, inverse tangent of parentheses. So linebacker 95 times 4.5 divided by running back 75 times 8.25. I get that angle is 34.6 degrees. All right, and as long as I draw this diagram and label that angle, we can, I know which angle you're talking about. That says 34.6 degrees. Can you read that? There you go. 34.6 degrees. What do you think? Fair enough? Doable? Okay, so let's see. Now the next question about this billiard shot here, I think I'll sort of leave, I'll leave for a different time. Okay? Yeah, I'll leave for that for a different time. Sorry, yeah, I think I'll leave this for a different time. Now, I know in your notes there's another question about my grandmother hitting someone with a shopping cart. That's kind of a pain of a problem, and I don't think it's worth it for us to do. I think that kind of question does not show up on the AP. Okay, so we'll leave that one for a different time. So hey, like I said, there's that question in there that's kind of a real pain in the butt. So let's bag that one. But I do want to add another one that I want you to try. It's a lot like the last one. It's an inelastic case. It's not this pool one. So you're gonna have to sort of bear with me while I'm gonna just post it in a new or put it in a new slide. I don't need you to necessarily copy the entire question down, but you're gonna have to probably pause and write some numbers down. All right. So just sort of hang out. I'll just keep talking as I do this. I'm gonna do this. Go here. Yes. Let's keep. We'll get to this one later. I'm gonna add a slide. Yeah. Copy this one. Here it is. I'll even make I'll make this nice and big so you can read it. Okay, so here's this question I want you to try to, well, I want you to do for tomorrow. So it's about, two objects approach an intersection, blah, blah, blah. They crash, right? They, blah, blah, blah. They, stick together, right, inelastic. And they have their skid marks go at a certain angle. I mean, this is literally how, some crash scene investigators that come and can look at this stuff, and literally this is what they do. I mean, they don't do the math; they plug it into a computer, of course. But I mean, this is how investigators can figure out things like, was one person speeding or was the other? All right, pretty neat stuff. So yeah. Now, you also tomorrow have a quiz on one-dimensional stuff. All right, so I'll say there, if you want to look in your text, I guarantee there are example or sample problems in there, more sample problems in the text for one-dimensional collisions. And one sec. I just wanted to get you a chapter and section number that you can look at. Looks like impulse and momentum is chapter 7. 195, page 195 to, collisions in one dimension is section 7.3, starts on page 204. All right, so there are definitely some examples in there you can look at. Okay? All right, folks, I'll see you tomorrow.